pleasure to introduce today our speaker, Zoran Škoda. He shall give a talk on the gluing bundle over non-commutative varieties.
So thank you for this opportunity to speak. So here by flag varieties, I will mainly go toward an example which is not like a quantum flag varieties, but some sort of a universal example, which is still not clear how to work with because it has some sort of up to homotopy properties. However, the coordinate kind of calculations are still well defined without any kind of derived things. So let me remind you that flag varieties first had these non-commutative deformations, which are kind of quantum. So if we consider G mod P, where P is parabolic, then there are things like SRQN, modulo Borel, and then you can take parabolics, and then you can take other types, and so on. And now we would like to have some sort of universal example, because all of these are in Faddeev-Reshetikhin-Takhtajan approach to quantum groups. And also in the classical cases, all of them are some sort of a matrix groups. So we would like to consider matrices with non-commutative entries as free as possible and make some sort of flag variety there. And then everything else would kind of embed inside. And then we would like to work with various bundles over such things and have various applications. I worked on coherent states in quantum group case. I computed various cocycles. On connections, I didn't work much. This theory, locally, you can put connections and how to glue it. This is kind of my business. This is still to be developed. And there was an announcement that I will say something about cross ratios at the end. Probably I will, but something doesn't work there. And I want to do everything, all of this from the very first principles of non-commutative algebraic geometry. What does it mean? So, sorry. I want to have general viewpoint. What is non-commutative analog of a scheme like in algebraic geometry, of algebraic group, of G-space, of quotient, of principal bundle, corresponding cocycle, associated bundles, and then specially do that in the case of general linear group and flag varieties of general linear group, but kind of universal non-commutative thing. And now, I want just to repeat for people who are not in non-commutative geometry, some of you are, what is basic idea of non-commutative geometry is that the space and its geometry is determined by collections which live over the space. So there are various kinds of objects which live over space: functions, observables in physics, bundles, sheaves, quasi-coherent sheaves, higher sheaves like stacks, and so on. And then we want to organize these objects into some sort of collections, like operator algebras, usual algebras, spaces of cocycles, K-theory kind of spaces, categories, higher categories, and so on. And these dual objects are with space in some sort of a dual relationship. There are reasons why this is good point of view, because in the usual geometry, you can really reconstruct the space from objects over that space. So there are some examples which you've heard, like Gale von Neumark theorem reconstructs topological spaces from C-star algebras. Giraud's theorem does that in topos theory. You get from category of sheaves, you get back kind of Grothendieck site up to some equivalence, but cohomological kind of properties are preserved. And then Gabriel Rosenberg theorem says that if you have abelian category of quasi-coherent sheaves on a scheme, then you can reconstruct back a scheme under some assumptions. And then there are various others, Stone duality, Tanaka duality, Bondal-Orlov theorem, Isbell duality, Serre-Swan theorem, and so on. These are examples. So they say that this is a valid point of view. And we want a specific kind of that, which is called non-commutative algebraic geometry, very general kind. And there are two possible approaches to this. One is that you replace a scheme in commutative case or in non-commutative, say, rings, non-commutative rings, but also some sort of combinations and more objects by some abelian category, which is in the case of scheme, quasi-coherent sheaves over scheme. In the case of ring, these are modules over a ring, possibly non-commutative ring. That's one point of view, that you have a category of sheaves, a quasi-coherent sheaves. And another is that you work with pre-sheaves on opposite of the category of non-commutative rings. And then among these pre-sheaves, you are taking some special ones which have some sort of a sheaf property, like in commutative geometry, but sheaf property has to be changed to something what is more general than grothendieck topology. I won't talk about that much maybe at some point, but it is important that we can even go between these 2 points of view. This to be mentioned at some point, but I will basically be in the first approach in this talk. So we chose this quasi-coherent sheaf version. And in this version, you see, we just let me say how from this version we could go to, in principle, to the second version. Namely, in affine case, that means affine case means that you are just working with modules over a single ring. It's just like an affine scheme. In that case, you can take the representing functor and this representing pre-sheaf. And these representing pre-sheaves can be glued. This gluing can be done by transferring kind of descent in this kind of geometry with categories into functors. So we cannot glue only categories, we can also glue these pre-sheaves basically by the same technique of descent. And for functors and for descent over localization covers, which will be very important for this talk, I have done some recent work with my ex-student Stoic and with Gabi Bem in 2011. She done wonderful work, but we never published any of this on this particular thing. Let me also remind you of one thing in background, which is very important for how we view these things. There is so-called Euler-McVatt's theorem from 1960, which says that colimit preserving functors, additive functors, among the categories of modules over rings are nothing else than tensoring with S over R, the extension of scalar functors. And other way around, if you have, and this tensoring is tensoring with the bimodule, because you take this this S as SR bimodule. And in general, if you are tensoring with SR module, you have a colimit preserving functor. But among those which come from extension of scalars, among all colimit preserving, I said something wrong. All colimit preserving functors are tensoring with bimodules, and some of them are extension of scalars. Sorry, and so Euler-McVatt's theorem says that all of them are tensoring with bimodules, but extension of scalars, that's additional remark, are those which are part of adjoint triples. So you have a direct image functor, you have inverse image functor, and you have direct image functor that has its own right adjoint. So these are, we call affine morphisms in this world of bimodules, or generally pairs of adjoint functors, which we call geometric morphisms in some other areas. So here we want to consider this this kind of thing, co-limit preserving functors in fact pairs of adjoint functors with some properties as morphisms among these categories which we consider. Now, very important kind of functors in this setup are localization functors. These are things which are, from which we infer kind of local properties. We consider local with respect to localization. There are other kinds of local with respect to flat morphisms and things like that. For my talk, it's important localizations. So in commutative geometry, you know that if you have a commutative ring, and then in commutative ring, you take an element, then you can invert it in universal way. That's a localization. And the spectrum of localization of a ring is so-called basic open sets, and these basic open sets form a base of topology of a spectrum. Now, in non-commutative case, there are very few sets which you can consistently invert. In particular, you can invert so-called ORA subsets. If you other examples are mainly giving bad properties. For example, localization functor is not flat anymore most of the time, and flatness is quite important for good properties. However, for our non-commutative flag variety, at the end of the talk, we will really need localizations which are not flat, in the sense that the composition of inverse and direct image is as an endofunctor is not exact functor. So what is Cohn localization or universal localization is when you invert in a universal way a set of matrices. So choose some matrices and you say, I want them to be invertible. And you look at the kind of universal ring, which has everything from before plus, so it has a map from the original ring to that ring, and every other map into some other ring where the images of this these matrices are invertible over this new ring, factors through this morphism. So this is so-called Cohn localization. It has been studied by P.M. Cohn. But very often this Cohn localization is not flat. However, it has one good example. If you one good property. If you look at the kind of coherent sheaves, that means you consider finitely generated projectives over a ring, then everything is okay. When you restrict to this category, then it's exact. And most of the time we work with some small bundles, like line bundles, some vector bundles, and these are examples of these. So this is good enough. However, if you want to represent a functor, then you want to have a pre-sheaf on all kinds of rings, and then working just with the coherent sheaves is not enough. You need much more if we would go there. So eventually one wants to make sense of spaces where one uses Cohn localization in a sense where this lack of flatness is compensated somehow, and that needs higher category theory, because for descent, that means for gluing parts of the space into a big space, you usually need flatness. Going beyond flatness usually needs some sort of a repair, and this repair happens by adding higher cells. So I don't know completely how to do it in the case of this non-commutative flag variety, but I have a program how to do that part. But this finitely generated projectives, everything works fine. So Cohn localization as this ring morphism from R to this universal kind of localization can be considered also as a localization functor. All these localizations like order localization, etc. I don't consider only at the level of rings, but even more as a functor. Again, this functor is one of those functors which I explained before, the functors which are tensoring by a bimodule. And it has its right adjoint. And we will play with such functors. So now, let me go now back. Let's assume that everything is flat. Then there is a way to say what is a scheme, at least for good schemes like semi-separated quasi-compact, completely functorial language. And that has been done by Rosenberg's paper in Composition Mathematica 98. So he considers a big category and the cover by several other categories, and this is covered by localization. So there are other categories together with inverse image functors. This is this Q lambda upper star from A to A lambda. Lambda is some finite set. Each has right adjoint. Both are exact. The second one is faithful. And they are covered in the sense that the morphism in A is invertible if and only if it's invertible, its image is invertible in A lambda for every lambda. This is kind of starting point that you can reconstruct A from A lambdas by descent. And from these functors, from the data among these functors. This Q upper star, Q lower star. So if you can go from A lambda to some A mu, so that from A mu you go back to A, and then from A to A lambda. So you combine these two functors to go between these pieces, and these data together reconstruct back A. And this, if so a non-commutative scheme is not just such a thing that you can reconstruct by descent the category. That's not enough. That's much less than a non-commutative scheme. But all these localizations have to be affine morphisms in the sense of adjoint triples. And the whole thing is relative to something. That is used in order to prevent some morphisms which are only bimodules and not really affine morphisms at some other places in the theory. So this non-commutative scheme is really a relative scheme. And in particular case, if this base is a category of vector spaces, that's the usual case, which will be kind of like a schemes over spec K, but we allow also non-commutative rings in the game. So locally, when you have additional axioms which guarantee that each of these A lambda is modules over that over some algebra over that ring K, such that C is vector is modulus over K. It's kind of trivial, but very carefully done, and there is a lot of subtleties which are, when you read his paper, looks trivial, but it's in a way very deep because he taught for many years. And whenever I'm confused about something, I go back to his paper and always find some hint there. I mean, it's unbelievable how much wisdom is in this little paper. As I said, this is a little bit more than just this descent picture. There is more than that. And I will just remind you that these local data of gluing these A lambdas, A mu's together, they can be assembled into one big end of functors from that you put the product of all these A lambdas, not from A lambda to A mu, but from product of A lambda to product of A lambda. An endofunctor, which is kind of comonoid in the category of endofunctors. We call it comonad. And this is the way to pack it. And usually people consider everything is easier when we pack it. In fact, you overlook certain things which can be seen when you consider really commodity as having pieces, and then when you add pieces or subtract pieces, then there is a pair of joint functors in enlarging and making smaller the cover. So if you have two different covers, then they kind of represent the same thing. If there are data, how to put them in a bigger cover, such that both inclusions into the reconstructed things of bigger covers are actually equivalences of categories. So it's not just that the things have equivalent, that from the descent you get equivalent categories, but you get them in a particular way, but via certain data plus some canonical functors induced by this data. We had last year we had quite progress in this with my collaborator Stojic. Now. The case of this Cohn type localizations, I said that it's enough, works well for finitely generated projectives. And if you want to do descent, you don't do these comonads, you do kind of infinity comonads. And for that, there exists so-called Bar-Beck-Lurie theorem. Bar-Beck theorem is the way you do descent in the usual case, and Bar-Beck-Lurie theorem does it in a infinity case. In fact, about the same time has been done by Kutsevich and Rosenberg in different language of different a infinities. Okay. So that is what is non-commutative scheme. Now we want to have a action, when action is principal, what is quotient, and so on. So we need much more picture in order to have the theory of bundles and cocycles. So first, what is a group? Well, group is if space is represented by category of sheaves, then the group is represented by monoidal category of sheaves. That's automatic. If you have a group, then the category of sheaves is monoidal. And not every action of monoidal category is really kind of geometrical. It's not really coming from an action of a group. And similarly, in generalizations like Hopf algebras also generate categories of modules, which are also monoidal. However, there needs to be additional thing. You see, before I said that you have to work over a base. Grothendieck was always saying work relatively. And in this base, in the category of vector spaces, you know what is a Hopf algebra. Over there, it's defined. And in fact, Hopf algebra is a comonoid in its own category of modules. So it induces a comonad. And this comonad, there is also version on the base scheme, which is just given by tensoring with it, with Hopf algebra, and using just the co-multiplication on this Hopf algebra. So similarly, in the group case and in other cases, so always you know what your object geometrically means downstairs, and then you lift it. So it's not only action, but action which lifts it in a certain way. I wrote a discussion of it in Georgia Mathematical Journal in 2009. There is very, very careful definition how to do it. Now I go back to the basics. So I was mentioning Hopf algebras. Hopf algebra is based on example that you consider functions on a group. So you know functions on a space just multiply. If it's a group, they also co-multiply. It's a dual operation. And example of these examples of when you have both operations are called bialgebras, and when you have kind of dual of inverses called Hopf algebra. I just here put the usual notation, and Svidler notation is a way to do it. I hope that most of you have seen Hopf algebras. I just remind in this context. So this S will be notation for the co-inverse, for the dual of the inverse, and delta of co-multiplication. So algebras have modules, co-algebras have co-modules. Also, those those co-monads, they are like co-algebras in the category of and the functors, they also have co-modules. So here, out of two pieces, you make one, and here, out of one piece, you make two. And modules over bialgebras have tensor product. That's the fact that I told you that you have a monoidal category. And in physics, this is related to being able to do multi-particle states. Now, if you look at the functions on the group, so if group acts on the space, functions on the group coact on the space, and the way is you just dualize this map. You have a reduced map on the functions, just post-composing, and then you use here some sort of a Fubini theorem or QNet formula, depends in which area of mathematics you are, that functions on the product are more or less tensor product of functions on G and functions on X, maybe completed in some areas of mathematics, like in operator algebras. And now coinvariants are the cases when this dual coaction is trivial. Rho of X is X tensor 1. And if you look at the algebra of functions on a set on which group acts, then coinvariants for the dual coaction are exactly the functions which are invariant along the orbits of the group action. That's very important for later part of the talk. Now, in the setup of G schemes, here up to now I was talking what is G space in the case when this space is presented by a single algebra. It's like affine scheme. What if it's given by gluing many categories which are modules over some algebra, each of them, but you glue them into some bigger thing. Then, as I say, you have this admissible action of the category of modules over Hopf algebra, but not any admissible action, but the one which is locally induced by coactions which you have, which I just explained in affine case. In affine case, you have coactions on algebras, which are algebra maps. In this case, there are some other cases possible. This is kind of the simplest case of the theory, and so you have kind of global actions which on affine pieces are made of familiar kind. Now, what is principal bundle? In classical case, you require that there is a right action of a group which is free and which has some continuity property and which comes automatically from local triviality. In algebraic case, it's also other way around under some technical assumptions. We call, so we can put all the data of a bundle in one map like this. Element-wise in kind of set case would be given by these formulas. And this can be dualized. And when you dualize this, you get so-called Hopf-Galois extension. And this Hopf-Galois extension is like a local case of what is a principal bundle. There are many other cases. There is more general definition, but this is what is usually studied, and like 99% of things in the literature about principal bundles in non-commutative geometry which are related to Hopf algebra talks about this. I almost never work with this because I have things which are not affine, so I need to have a category where locally I have this Hopf-Galois extension. So I have kind of globalized Hopf-Galois extension. This is kind of my main subject, that all the time you have something big, which in affine pieces reduces to things like this.
Zoran, what do you mean Hopf-Galois extension?
So Hopf-Galois extension is algebra, which has a coaction of a Hopf algebra. which is algebra map, and such that if you take this particular map, then this map is invertible.
Why is it called Galois extension?
Why it's called Galois extension? Because if H is, I guess group algebra, or it's dual. I'm not completely sure what's the example for classical Galois theory. Then usual Galois extension give you examples of this, provide examples of this Hopf Galois extensions. And if you look at the Galois correspondence, that this Galois correspondence is related to certain categorical notion in this Hopf Galois case, that which is geometrically meaning that if you take a space with which is a principal, if you take a principal bundle and take equivariant sheaves over the total space, this category is equivalent. That's called descent along torsor or torsos or Galois descent to usual sheaves over the base. So if the base is reconstructed from the category of sheaves, then the base of a principal bundle considered as a G space, then it's enough to just consider these equivariant sheaves. And that's the perspective which I put here practically as a definition. And look when it gets when it has good properties. Okay. Okay.
So if anybody has question, do you like that they interrupt you or check after your talk?
Yeah, you can interrupt. It's better to control me, because otherwise I will start talking just for myself. So here I'm really talking about this idea that if you have a space with G action, but now G is not just a group, it can be a Hopf algebra and any kind of symmetry object which is given in this setup. And in this setup, I say that the general thing is that you have a comonad induced by Hopf algebra or group or something. So G is not anymore group. G is like a replacement in this setup, which is a endofunctor with some properties which represents geometrically admissible action. This fits very well with examples. So if you look at, then if you have such a thing, then you can define what equivariant objects are, which are equivariant sheaves. If you know what are sheaves, then you have additional structure on them. These are some sort of comodules over this G, if G is a comonad. Then you look at the category of comodules, and it defines a quotient stack. That's the basic idea. But this quotient stack can be that you don't have good coordinates on it, so you can't really work with it. But in good cases, it has. And in fact, Gabriela Bem helped me in 2011 to kind of fulfill my dream from 2004, when I had some failure in one part of the proof, to prove that if you start with the non-commutative scheme of Rosenberg, together with the G action, such that locally on each of the open sets of each of the affines, you have a Hopf Galois extension. Then if you look global quotient, and you look of each of these quotients, then all these quotients glue again into this global quotient, and this gluing is again making the structure of non-commutative scheme. This requires a lot of yoga of adjoint functors, etc. But it basically tells you that if you have a principality in this very general sense, if you have a principal bundle, and you have a total non-commutative scheme, then only local property guarantees that you reconstruct the base, which is also non-commutative scheme. In this talk, we would like this connection to go other way around, that the base is a scheme, and that you give some data, like a cocycle, and that you can reconstruct the action above, and that this action is a principal bundle. Okay? So let me say here, there is some notation. You see, you have this functors q lambda, well, I guess it should be upper star. This q lambda and q lambda g, this composition is the same as g lambda q lambda, if such g lambda exists. So then it is because q is localization, so it has a reflection, it has a right adjoint which is fully faithful. Then this G lambda is unique if there is isomorphism like that. So this G induces this G lambda locally. And other way around, if you have this G lambda locally, and if you provide the data of this natural isomorphism between G lambda, Q lambda, and Q lambda G, then this enables you to say that such G is unique. So you can glue things if you have additional natural transformation, such natural transformations with some coherences, we call them distributive laws. So certain distributive law is necessary to glue the things. So this is kind of the origin of cocycles. But this is at very abstract level. It's just at the level of functors. I want really to take algebra data, bimodules, and from them to construct a cocycle, not at the level of functors, and this is too much. But here you can analyze theoretically. You can start here. Here it's very clean. You can think of it very cleanly, very generally, and then you go to very concrete data and do it very very concretely. Now I am to this principle I told you, this Galois kind of theorem. That equivariant sheaves in this case are, or in the case of just Hopf algebra and just a co-module algebra over Hopf algebra, that means you have a coaction which is algebra map, then you can consider this category of modules over E which are in the same time co-modules over H in compatible way. This is the same as modules over the invariants. That's example of this thinking that equivariant sheaves are just sheaves over the base, provided this E is Hopf-Galois extension. So that means faithfully flat. That means faithfully flat Hopf-Galois extensions are really such that this quotient stack is really affine, and it's affinely embedded. You see, these coinvariants embed as a subalgebra in E. So this is a general. Rosenberg suggested to me, it's in general, principal bundle is just when I have admissible action of a monoidal category on a category, and the forgetful functor from equivariant sheaves to quasi-coherent sheaves is an affine morphism. And that's it. No complications in affine case. There are all these Hopf-Galois conditions, such and such. This is extremely simple. Nobody studied this. This is a proposal. It works in simple cases. It should be systematically studied. Here, I don't require any covers, every non-commutative scheme, no local conditions either. It's very appropriate. This is some sort of Galois condition at a very abstract level. Now I said that abstract cocycle, for abstract cocycle, you need to glue these local pieces via some sort of two cells. Let me go further. Now, Hopf-Galois is nice, but it's a little hard to work concretely with cocycles, because this property that is invertible and you don't know what is the inverse, remember that map in Hopf-Galois was invertible, you want to construct it very concretely. So for example, if you have a principal bundle which is trivial, we want to glue everything from locally trivial pieces, then there is a section. There is a global section. Global section means that you have a trivial principal bundle. if you dualize so this T will be T from the projection, and tau is this division map for the principal bundle. Then from that you can define from every function you can get a new function given by this formula. And this will go from functions on G, on a group, to functions on a space. So from a Hopf algebra to an algebra. And this kind of section we call a cleavage in non-commutative geometry. So every such cleft extension is Hopf-Galois. But it is a little better. I have very concrete data. And in examples, like some canonical bundles over flag varieties, usually have such a situation. And you don't even need that this is algebra map, but it needs to have other properties. That is convolution invertible and it's comodular map. And that's enough for most of the theory. I will usually take that it's algebra map. That's in examples, but you need less. Let me jump a little bit. Now, if you have this cleavage, then cleavage induces map on coinvariants. If U is coinvariant, then you can do gamma of H1, U gamma of S, H2. S is antipode, and H1, H2, tensor H2 is the coaction of H. And this thing is like, it's like conjugation. It's like something like inverse of something. It's not quite, but almost like conjugation. And from U, which is coinvariant, you get again coinvariant. That's easy. And then they satisfy something what we call measuring condition. So now this is nice. You see, if I have a cleft extension, I have coinvariants, and this gamma is isomorphism between H and some piece of E. This is kind of this is 1-1 map. It's not surjection, but it's 1-1 map. So this is like a fiber, and the coinvariants are like a base. But it's not just a product. In classical case, a trivial bundle is product. Here is not a product. Here is a product, but there is as a tensor, as a space. But as an algebra, it has more complicated. It is so-called smash product, and this structure comes from this action. If gamma is not an algebra map, but just the other thing, then it's then this is not an action, but it is still a measuring, and then it's not a smash product, but it's a so-called cocycle cross product. So there is additional cocycle which is local there. Now this is on one affine piece. Now I want to combine this affine piece. I want to see what is in between them. So if one of them has a U and gamma, another has U and gamma, and I want to compare these gammas on common intersection, but this is not sets. Instead of intersection, I take localization functor, and localization functor ends is kind of comparing intersection, and there are two intersections because localization functors can compose in two different ways. So there are two essential images, so one composition and another composition. When I take okay, let me not go into details. And then you see, so what I have on the base, I have these base algebras, which we glue by some data, by descent. As I was saying before we had any actions, it's just usual gluing. But in order to have the data that we can really make a bundle on it, then I have this local action, which I explained how it came, which came because it's cleft. And then if you compare the two, then there is a bimodule which is useful for comparing on every. So if U lambda mu is a common intersection, that is actually this essential image of a composition of certain localization functor and functors, then this is another property And for gluing, we have this, as I say, we had the comonad before. So this is like a double intersection. This is like a triple intersection, but it's not intersection. It's a tensor product of algebras. And now the cocycle condition is this equality. I was very happy when I found this in 2011. In this generality, I knew cocycle in some special cases, but this is kind of very beautiful. You see, you have a co-multiplication on edges here. This would be G and G if it's group element, but here's Hopf algebras. And this delta is for gluing. So it's interplay between the coaction for gluing and coaction for the Hopf algebra. So kind of a group structure, the gluing inside the group and gluing inside the space are intertwined. And this is a generalization of the usual gluing. You can compute for commutative spaces, and this will give you the usual gluing. It's a really kind of unexpected that something like that will be a cocycle condition. It has, in special cases, it can be maybe more understandable, but I think it's very beautiful. It's very beautiful. And the transition functions in special cases, under certain assumption, which I won't explain now, you can reduce this data to considering those local actions, measurings, they still have to exist for each of the pieces which you glue, but in between you have like these maps from a group to common intersection, kind of like it's a bimodule of common intersection. It's not algebra functions, it's a bimodule. And which is given by comparing two sections. You know, when you have one, gamma is, in commutative case, comes from a local section. So if you have two local sections, you compare them, you get a transition function. And here you dualize, and in this combination, you can get some sort of dual transition functions, and they satisfy kind of, again, this is some sort of, you see, this is a cocycle condition in this special case. This is most of the time enough. It looks very similar like in classical case. You can do similarly for associated bundles. Namely, in associated bundle, you have typical fiber, which is left module, here left co-module in the case of Hopf algebras. And then you do so-called cotensor product. You can go from algebra, tensor, typical fiber, in algebra, tensor, Hopf algebra, tensor, fiber in two ways. One is that expand by coaction the first guy, and another the second guy. And you look at the equalizer of the two. That's locally. And then you have to glue again by descent. There is the whole technique which I developed. First examples in 1997 and then 2002, and there is some examples in 2007 on coherent state paper. But I never really published a general version. I kind of find it trivial, but I should really explain this to people. Okay, now we have to go to examples. I have only 12 minutes. So remember linear groups. I want to have some kind of non-commutative analog. So what is Hopf algebra on a linear group? Well, I take functions on these are like matrix entries as functions of the matrix. They also, with this, these entries as certain functions, you can also play determinants and things like that, like for the usual matrices. They form a bialgebra, and this is the rule. Instead of multiplying, this is like a multiplication rule of matrices, is this, you go other way around for functions. You just dualize. And this is a matrix Hopf. We call such things matrix bialgebras, and matrix Hopf algebra is a little subtle version of that. Now, if you have a matrix whose entries are non-commutative rings, then determinants are not good thing, and determinants are needed to do calculations. So there are certain rational functions which are called quasi-determinants defined inductively. with which you can do such calculations. These are like entries, like inverses of the transpose of the entries of the transpose of the inverse matrix, but defined in a magnificent way discovered by Gelfand and Retakh. And now, if you look at the matrix, then you can consider. Let me say, you see these quasi-determinants, you have them n square quasi-determinants. You have to distinguish one element which is distinguished, and then you will have a different quasi-determinant. All these quasi-determinants are kind of related one to another. They are so-called homological relations, but basically you have to distinguish one. So if you take these stars here, then and take this as distinguished. So this stars is a certain minor, and you have this here. Then this quasi-determinant gives you a formula for a part in the Gauss decomposition of a matrix into lower triangular and upper triangular one. And this is for I take that the Borel will be lower part, and I will decompose as upper triangular unidiagonal times lower triangular. I call this Gauss decomposition. And these entries here, if you take this matrix with this quasi-determinant and this minor with this quasi-determinants and divide these two in certain order, this ratio will be coinvariant on the quotient, which is defined by help of starting with the matrix Hopf algebra and then taking all this upper part to 0. You will have this lower triangular will be a quotient Hopf algebra, which coacts on the whole thing. This is like action of a subgroup on a group, dualized. And then a chart on the quotient will be given by entries which are ratios of such quasi-minors. These are called quasi-determinants or quasi-minors. And such ratios are also called kind of Plicker coordinates in non-commutative or quasi-Plicker coordinates. So you are solving simply linear algebra problem, but over a non-commutative ring. And these are these solutions which I just explained pictorially. And now we want to have a free case that we take a matrix by algebra, which is generated by free associative algebra. So we have n square generators with no relations. But you want to be a Hopf algebra, so you need to have antipodes, so you need to invert this matrix. And then there is a phenomenon that in non-commutative case, the inverse of transpose and transpose of the inverse is not the same if the entries of matrix are non-commutative. So you need also to take transpose and its inverse and so on. So we'll have to add a lot of additional generators, but let's not think about it. The only thing important is that you invert. So this is also Cohn localization. You do Cohn localization of certain of a free associative algebra, and with the structure of like matrices, the entries of matrices, the non-commutative entries. The same thing you can do for quantum groups. Some things are better, some things are much harder in quantum case. And you have this, Borel is coacting. There are formulas for this, and then there is a theorem. This is one of things early in my career. For quantum groups, it's very difficult to prove this. For free case, it's kind of easier. So what I say that if you take Gauss decomposition, the Gauss decomposition gives you the formulas, these gammas. You see, you have the formula for gammas. That those B's of the quotient Hopf algebra of the Borel go into corresponding entries coming from the Gauss decomposition. So Gauss decomposition is in the localization in which you have sufficiently many inverses that you can do the Cohn localization. And that is a universal such one. And see, this formula here is a map of B co-module algebras. It's 60 pages of calculations for say, SLQN. 60 pages of calculation, very difficult. But for non-commutative, for free case, it's almost trivial. And the fact that it quotients in this subvariety corresponding to the usual flag variety, and then the other part, this U part in Gauss decomposition, its entries are coinvariants. And from these coinvariants and this gamma, you can reconstruct the cleft extension. So you have locally a principal bundle. If you, the whole thing multiplied by a permutation matrix, this is like a shifting by a Weil group element, then you have another trivialization. And all these trivializations make a cover. And the same thing works for parabolics. You take block matrices, parabolics, and the same thing works. So really you have some sort of a quotient which is universal, very big. You have no relations. It's not a quantum case. And you have all the machinery from before. You have those gammas. From gammas you get that action. From this action you get that cocycle, you remember. So all those data can be computed from this, and this computation comes from quasi-determinants. There's very concrete computations with quasi-determinants. So we can compute everything. You can do that for Grassmannians, no problem. For Grassmannians, you would have a block matrix, which is like 2 times 2 matrix, maybe not everything quadratic, but say if it's n in 2n, n planes in 2n dimensional space, then all of these quadratic matrices. But this makes sense, the composition in that case also. And then you can take entries of this, and this will be again some sort of Plücker coordinates. Now with these Plücker coordinates can be done many other things. And one of the things I wanted to do in this talk, and I kind of didn't succeed because I saw that I have some errors this weekend, is to compare the cocycle, which is for this canonical bundle, like GLN non-commutative over non-commutative universal flag variety. You can associate bundles to everything. You can do various things. You can compute it. You can compute cocycle for this particular open sets. And I wanted to shift this a little bit to get a non-commutative generalization of cross ratios obtained by Gelfand and Retakh, and studied recently in much more detail by Retakh, Sharygin, Volodya, Rubtsov, and so on. And they, you know, the usual cross ratio is invariant of projective transformations. If you take 4 points, then this ratio doesn't depend on which homogeneous coordinates you take. And you see, there is, this expression can be generalized, but it's ad hoc. It's just algebraic to expression which utilizes this Plücker coordinates for exactly Plücker coordinates which appear here for Grassmannian 2,4, non-commutative universal one. And then many identities hold, but there is no geometrical interpretation. So I wanted to have a geometrical interpretation. That this is, because in classical case, you take this, you take the tautological line bundle, tautological principal bundle over the Grassmannian, and take the cocycle for it and compute it for certain neighborhoods. And these neighborhoods will be indexed by, they will be indexed by choice of a flag, that you don't take the canonical flag, 2 spaces in 4 spaces, but you take some choice. And if you take 2 different choices and compare on transition function, you get you get a cross ratio. And I wanted to do the same here. So that would mean that I'm not doing the decomposition, this Gauss decomposition for this canonical, those W neighborhoods corresponding to the shifts by Weil group elements of the main Gauss, main Brucha cell with canonical Gauss decomposition. But I would like to shift them by, instead of taking the generating matrix G, I multiply this G by another generic matrix. So if I do it by invertible numerical matrix, everything is the same, nothing changes. But I want to have a generic matrix so that the coordinates which enter via this generic matrix would again be the data from the same algebra. That all the identity will be from the same algebra. However, of course, to determine a flag, you don't need to really have the whole basis. You don't need four guys. It's enough to have two guys. So because the other two, the applied coordinates won't see the whole change of coordinates, but just a part of it. So one matrix O can come from one copy of two generic function, two generic elements in a free associative algebra, another from another, and then you get a transition function which is not just an element in algebra, but has also parameters in O and O prime. However, there are some things that I was not completely consistent, because these are not, what does it mean parameterized? You work with non-commutative thing, you have to change the coordinates. And the change of coordinates would be via numerical matrix. If it's not numerical matrix, then of course you can do you can replace, because you do functional, you can replace by coaction, but then this part commutes and you want the whole thing not commute. You can do a free product and then everything doesn't commute, but then the computation doesn't work correctly. So there should be an appropriate combination which works. I still didn't succeed completely, but I think this should work because it works in classical case. Although in classical case, usual geometric picture, how this is explained is completely different. It's not via this bundle, it's usually via certain kind of parallel projections among the flags, among the subspaces which determine the flags, among certain using polarizations which correspond to this data. But as I say, I'm sorry that at the end I didn't straighten it up. Something didn't work correctly, but I think it should work at the end. But maybe I'm wrong. I don't know. Okay. That was what I wanted to say today. Maybe it was a little too much. Hello?
Thank you. It was very interesting. Just can you show?
Thank you.
Sorry, Zoran.
I have a question.
Wonder whether you can show some. May I ask a question? Sorry.
Yes.
Yes, please.
I'm sorry to disturb. Yeah, just wonder if you can show what kind of computations you had in the end. Do you have some slides with the computations? So what kind of transition
I don't, because
eventually?
I think it's embarrassing, because there are things where I kind of where I thought that I'm doing it right, but now it looks like I'm cheating. But it's quite complicated computation, because you see, you have to do this gamma to -1, but the arguments are having co-multiplication inside. So it's a sum over certain matrix indices. There is inverses of matrices and so on, and you take matrices of those entries which come in Gauss decomposition, overshifted generic matrix, So it has complicated expressions which go into these summations and a lot of matrix indices, a lot of matrix computations. It's very long.
I see.
It's far more than I expected
So
when
really,
I had first idea.
yeah.
So probably there
really
are
would
places
love to see the
for
details.
improvement, probably.
Yeah. Maybe next time. Okay, thank you. Sorry for butting in. Sorry.
I
Zoran,
have a
can I ask you
question.
Please,
Yes.
please.
I have a question. Can I ask?
Yes, yes.
Hi, Zoran. This is Rita. How are you? Rita
Hi,
Fioresi
hi.
from Bologna.
Okay.
I immensely enjoyed your talk. As you know, I have a very strong interest in this. And I was very interested in this cocycle, right? So if I understand this correctly, when you have this, thank you. This cocycle is encoding the gluing condition, right? So you have this data and you want to glue it. So I was wondering, see, what if you think classically you have proj, right? Proj is a scheme that gives you the information all together, right? And as you know, I'm interested in the quantum proj. So when you glue, do you get some global object that encodes also the projective embedding on your flags? Because when you speak about Plucker, somehow you have that encoded somewhere, right? So you understand my question?
Yes, yes.
Okay,
Well,
thank you.
You see, this technique does not presuppose that you must have a quotient which is
Of course,
projective.
yes. Yes, of course.
Now, if you would like to have this data in terms of kind of graded data, then you would have to have some sort of Borel veil. And of course, in quantum case, you have such things. But in this universal case, when everything is free, then there is something something what is quite surprising. You have more characters. Namely, when you have this Borel, or when you have like a total part, then basically the elements of on the diagonal, which have to certain power, they don't need to commute. And you have additional kind of characters. Now, what is their role? They certainly mess up the usual Borel veil picture, but maybe, I mean, it looks like so. It is very strange that nobody studied these characters, because you can take a different kind of point of view. So you see, Kontsevich and Rosenberg considered also kind of universal non-commutative flag variety, not mine, but a little different. They wanted to consider a pre-sheaf into groups. So it's really pre-sheaf into groups. It's not Hopf algebra. And they also have Cohn localizations, very similar picture. They don't have this many inverse of transpose of the inverse. They have just two. So it's in a way killing a little bit because it's only two. And it is somehow, I was convinced, you see, they didn't succeed to have this. I mean, their purpose of their construction was to explain identities among quasi-determinants. There are many identities in terms of this geometric data, and I can explain that. So they didn't. So I was thinking, look, my approach is better, but now I'm not convinced anymore, because I think their example can also be modified to that. And if you modify that way, if you have a pre-sheaf on rings, then you can really evaluate rings. That means you can consider real matrices, not functions on the matrices, real matrices with entries in non-commutative rings, which parameterize things, and consider like a group characters of that, not the co-characters in the sense of Hopf algebras. And again, I see these same new characters. So this is like non-commutative pre-sheaves with values in usual groups. I would expect that somebody considers such non-commutative GLN and characters for it, and there is nothing in the literature. I mean, it's very surprising.
Okay, thank you. Thank you.
So there is more question, please.
I have a question. Hi, Zoran. In this non-commutative free setting, do you have, for example, for Grassmannians, some analogs of decomposition into Schubert cells and these topological interpretations?
Well, even in quantum case, I didn't study that much because you see, when you have localizations, you are not making quotients of algebra. You are making embedding into bigger algebra where there are some inverses. And this localization and taking quotient algebra, they're taking like a subvariety, taking closed one. So taking open and closed things, this combination is a tricky thing. So some people work with closed things, some people work with open things. Combination in non-commutative case, that's so much harder theory that I hope to do it one day. You see, for these reasons that I was doing computations, for example, I said that 60 pages you need for that theorem of mine in the quantum group case. So over there, I had to prove certain results. And some of these results were used by some of these people who work on this kind of Schubert cells, like straightening calculus and things like that. There is like a recent recently Tom Lenagan and some other people, they used it for saying something about quite different perspective on Grassmannians, which is not only about quantum groups, but about kind of things which are more related to things like quantum cohomology and things like that. So this kind of geometric approach, which comes from symplectic geometry, is very rich. And quantum groups, you are doing something formally, and there are places where things kind of fit together. And this is beyond me, but it's very interesting to me. I would like to do it in future, but
because
sorry. So could you tell me a little bit more precise the relation between quantum group and what you're doing here? Not quantum cohomology in symplectic geometry. Because
well,
I remember that is a...
as I said, some calculations in, say, quantum Schubert calculus,
yes,
depend on combinatorial properties whose proof requires combinatorics which is coming from these calculations which were first developed in quantum group case. That's very surprising to me, but there are results like that.
You mean that quantum cohomology on graph on flat manifold?
Yeah, there are some
very long time ago,
combinatorial properties which are kind of shared, and not shared that it's excellent, but it seems that it's deep thing. So I see that people consider these geometric things which are related to Poisson geometry, symplectic geometry, etc. And there are now some corresponding places where it fits.
Yeah. Okay. So, so you have some more questions,
maybe
right?
it's only maybe there is some deep combinatorial thing which is related to both, which is maybe not nothing geometric, but I don't know.
So yes, somebody have some more question?
Yeah, I maybe have one. If your Hopf algebras become quasi-triangular or quasi-triangular, does it simplify a picture in a way? Could we recover some additional data from
I don't
address?
know. I don't know. I mean, not from first principles, but I don't know, maybe.
Well, I was looking on exactly these slides when these measurements no longer an actions. Maybe if you go to some braided multiplications, it could help.
Well, of course, well, I mean, it's a little different. You see, braided groups is one thing, and the difference in generalization between the smash and cocycled cross products is a different thing. So this difference between measuring and action is like a difference between cross product and cocycled cross product. So it's different than going into braided version.
Yeah, I see. Okay, thanks.
Okay, chat. Yes, so if there are no more questions, let us thank speaker again. And Zoran, please don't forget to send me a slide, okay? So you can share to all the people.
Okay, thank you very much.
Yeah.
Thank
So
you very
let us
much, Zoran. It was very interesting. Thank you.